All right, this is section 8.3, and I'm going to assume that you guys know how to do the integral. Let's just set all these up. The region between the graph of f of x equals 2 plus x cosine x and the x-axis over the interval negative 2 to 2 is revolved around the x-axis to generate a solid. So the curve goes from negative 2 to 2. So here is f of x right here. Now, we're going to rotate this around the x-axis, and the radius goes, it's up against the x-axis. So the radius is going to be the function value. So the function value right here is the radius of this circle when we rotate this around the x-axis. The function value for this one is also the radius when we rotate this one around, and so on. Now these circles are stacking up along the x-axis, so we're going to integrate with respect to x. Now let's say that we took a curve, some curve, and if we wanted to find the area, let's say from 1 to 5, we would integrate the curve. So whatever f of x is, dx, but dx, this is really length times width of a rectangle. So integrating a one-dimensional figure, just a curve, gives you 2 dimensions. So likewise, if you integrate a 2-dimensional equation, then you get the volume. You get the 3rd dimension when you integrate. So we need to integrate a 2-dimensional function, a function that represents 2 dimensions. And in this case, we're going to integrate area. Now, the area of the cross sections are, well, they're circles. And so we're integrating pi r squared. So pi times r squared. But we need all of these r's. Well, all of these r's are following this curve right here. They're following f of x. So we want 2 plus x cosine of x squared. I'll assume that you know how to do the integral part, so we're just going to set these up today. The region in the first quadrant enclosed by the y-axis in the graph of y equals cosine of x and y equals sine is revolved around the x-axis to form a solid. Find its volume. Well, now the radius is in between. Actually, the 2 radii are in between. How do I want to put this? We're doing washer here. Let's do what I call the 180-degree turn. So like this, and maybe like this, something like that. So here's 180 degrees. We have this circle right here, and we have this circle at this given x value right here. And the area is in between these 2 circles. So it's the big circle, big, not dig, big circle minus the little circle. And it's a washer. So this is the washer method to find the volume. And the area is in between. Now, the example up here, the area is up against the radius is up against the x-axis. We don't have 2 functions. This one we do, and the area is in between these 2. Now the cross section is still a big circle. If we took all of this area right here of the big circle and we subtracted out the area of the little circle, we'd have the area in between, and that's what we're trying to accomplish on this one. So now let's find the area of the big circle. Well, the area of all the big circles, they're stacking up along the x-axis, which means we're going to integrate with respect to x. We want pi times the big radius, pi r squared big radius, minus pi r squared, and this is going to be the little radius. Well, the big radius goes from the x-axis to, this is going to be cosine. The top one is cosine. So this one is cosine x squared, and this one is sine x squared, the little radius. The little radius is going to sine. Now, when I integrate these, I always factor out a constant. So we have cosine squared x minus sine squared x dx, but cosine squared minus sine squared, I can go a little farther with this one. Oh, and we're integrating from 0 to, don't they meet at pi over 4? This is cosine of 2x, and that'd make it much easier to integrate this, or that's how you would integrate it, because this is the formula for the double angle for cosine. Now, this is not a volume of rotation. This is just a cross-sectional, known cross-sections. A mathematician has a paperweight made so its base is the shape of the region between the x-axis and one arch of the curve y equals 2 sine. So here's y equals 2 sine. Excuse me. Each cross-section cut perpendicular to x-axis. Perpendicular to the x-axis. So these cross-sections, they are stacking up along the x-axis. They're perpendicular to the x-axis. And hence to the xy plane is a semicircle whose diameter runs from the x-axis to the curve. Think of the cross-section as a semicircle fin sticking up out of the plane. Find the volume of the paperweight. So these are semicircles. They're 1/2 pi r squared. That's the area. And if you integrate the area, if you integrate a two-dimensional, an equation that represents two dimensions, you're going to get the third dimension when you integrate. So we're integrating from 0 to pi. And I usually pull the constants out, 1/2 pi, and then we need r squared, but dx. We're doing this with respect to x because these are all adding up along the x-axis, and in theory, there's an infinite amount of these cross sections, and that's what integration is all about. It's adding up an infinite amount of stuff. All right, well, it's 2 sine x, 2 sine of x squared. There it is set up. That'll be 4. When you square it, so if you pull that out, it's going to be half of 4 is 2, so 2 pi, 0 to pi of sine squared x, and then you need, the power reduction formula for sine to actually integrate this. In exercises 7 through 10, find the volume of the solid generated by revolving the shaded region about the given axis. About the x-axis. Well, these are stacking up along the x-axis, and this is how we'd rotate it. Here's the 180-degree turn, and we'd rotate around the x-axis. Now, if they're stacking up along the x-axis, then we're going to integrate with respect to x. So we need this to say y equals 2y is equal to 2 minus x, y is equal to 1 minus 1/2 x. And those cross sections are circles, so we need to integrate pi r squared, which is 1 minus 1/2 x. Number 8, we're rotating now around the y-axis. So these cross sections are still circles, and now they're stacking up along the y-axis. So we need to integrate with respect to y. Well, this already says x equals. When we integrate with respect to x, we need to see y equals. When we integrate with respect to y, we need to see x equals. Now, these are circles, and the radii are following the curve. But when you have x equals, you get the y, and you find the x by plugging the y in. So when you pick this y, you find the x by plugging it in, and that's going to be the length of the radius at that particular y value. Now, it's still pi r squared because these are circles. So we have an equation that represents the two-dimensional surface. When we integrate it, we get the third dimension. And this is just going to be 3y over 2. So you're integrating from, I should put this, 0 to 2. On number 7, you're integrating from 0 to 2 as well, but 0 to 2 along the x-axis. And this is going to be 9y squared over 4. And I'll assume you guys know how to integrate that. 9 about the y-axis again, and it says x equals. It's set up for us already. So the 180-degree rotation would look like that. We're going to rotate around the y-axis. So we're around the y. Around the y. It's perpendicular to the y-axis. So that means we're going to integrate with respect to y. Again, these are circles because we're rotating around. And this is going to be pi r squared. So pi tangent squared pi over 4y. And now we're integrating from 0 to 1 because we're rotating these around the y-axis. And 10, let's see. Rotating about the x-axis. So here's the 180-degree turn. We would rotate this around the x-axis, which means we're going to integrate with respect to x. And so this is going to be pi r squared again. It's kind of all the same stuff. This is sine of x, cosine of x. And We have to go from 0 to whatever this 0 is. Let's see. Sine is 0 at 0. Sine is 0 at pi. I believe this is from 0 to pi. In exercises 33 and 34, use the cylindrical shell method to find the volume of solid drained by... okay, so you guys don't do cylindrical shells. Let's see if we can... Yeah, we're not going to be able to do this one. We could... You guys could rotate this around the y-axis without using... does it have line y equals 1? The x-axis... Around y equals 1. No, have to do cylinder. Never mind. You got to do cylindrical shells for this. That's a BC topic.